In the previous video, we obtained an expression for the orbital speed of a satellite, and the equation that we got was v0 is equal to square root of gme upon r, right? G is the universal gravitational constant, mass of the earth, and distance between the center of the earth and the satellite. So this was the expression that we got. The other expression that we used was gme is equal to gre square. Right? This is another expression that we used. I mentioned them over here because we will be using them in this video while we try to get an expression for the period of revolution of a satellite. Right? So let's start off. So we're trying to find out the period of revolution of a satellite, right? So let us say, I'll draw a very simple diagram over here. Let us say this is the Earth, right? And let us say this is the circular orbit. I may not get an exact circle, but for understanding purpose, this is sufficient. So this is this is the orbit in which this particular satellite is revolving around the Earth. We have taken this distance as small r, the distance from the center of Earth to the satellite. Right? The radius of the Earth is re, and mass of the Earth is me. Right? So this distance is r. That means the distance when it completes one revolution will be 2r. So distance covered by the satellite in one revolution would be 2 pi r. Right? This is the circumference of the circle. The speed of the satellite we know is v0. Right? Speed is v0. Therefore, the time period, the time required to complete one revolution would be distance upon speed. Distance is 2 pi r and speed is v0. Right? Therefore, I get this expression: time period of a satellite is 2 pi r upon v0. Time period of a satellite to complete time period of a satellite is 2 pi r upon v0, where r is the distance between the center of the Earth and the satellite, and v0 is the orbital speed. Right? Now we have obtained an expression over v0, so I'll substitute this value of v0 in this equation. Right? So I'll get, therefore, t is equal to 2 pi r upon, for v0 I'll write square root of gme upon r. Right? Now r is equal to re plus h, radius of the Earth and height, so re plus h. So I'll put that in this equation. So I'll get 2 pi re plus h upon square root of gme upon re plus h. Okay, as I work with this, re plus h, square root of re plus h will come in the numerator, so I'll get t is equal to 2 pi re plus h into square root of re plus h upon square root of gme. Now what is this? Let us go back to some math, very simple math. We know that a raised to 1 into a raised to half, that is a raised to half is of course square root of a, is equal to a raised to 1 plus half, that is a raised to 3 by 2. Okay? A raised to 1 into, that is a into a raised to half is a into 1 plus half by law of indices, and this will give me a raised to 3 by 2, and this can be written as a raised to 3 half, right? And therefore this will come out to be, this can be written, half is square root, so I can write down square root of a raised to 3. So if I have a raised to 1 into a raised to half, that can be written as square root of a cube. Similarly, here I have re plus h and square root of re plus h, so it's like a into a raised to half. So this particular expression now will take the form, t is equal to 2 pi square root of re plus h whole raised to cube upon square root of gme. Right? And of course I can have only one square root sign, so I can write this as is equal to 2 pi. Okay, there's shortage of space over here, so let me just cut this out and I'll go over here. Right? So t will become equal to 2 pi into square root of re plus h whole cube upon gme. Right? So this is equation number 1. I can get another equation for the same thing by substituting for gme gre square. Gme is gre square. So if I put this gme gre square over here, I'll get one more expression. So I'll write down that expression is equal to 2 pi square root of re plus h whole cube upon, for GME, GRE square. So GRE square, equation number 2. Okay. Let us now look at this equation 1 again. What is the mass of the earth? The mass of the earth can be written as 4 upon 3 pi r e cube into density. Where did we get this equation from? Mass of the earth. Mass is volume into density, and earth is a sphere. So this is the expression for volume of the earth, 4 upon 3 pi r e cube into density. So I can put this particular value over here, right? So P will become equal to 2 pi square root of r e plus h whole cube upon g, and this is into 4 upon 3 pi r e cube into rho. This is cube. So this is the expression. Now I'll try to simplify this. Is equal to 2 pi into square root of r e plus h whole cube upon, this 3 will come in the numerator, so I can write multiplied by 3 over here, right? And this is 4g pi r e cube rho, right, is equal to, I'll take square root of 4 pi outside, right? So 2 pi upon square root of 4 pi into square root of r e plus h whole cube multiplied by 3 upon g r e cube into rho. Right. Now what will happen over here? This is square root of 4 pi. Square root of 4 is 2, so 2 will get cancelled, and this is square root of pi and this is pi. So I will have square root of pi in the numerator, and if I have square root of pi in the numerator, I can get it back into this particular square root sign. Let me repeat what I said. Square root of 4 is 2, so 2 and 2 will get cancelled. Here I am left with square root of pi. Square root of pi, pi divided by square root of pi will be square root of pi, and that I will shift inside. So this expression will take the form 3 pi r e plus h whole cube upon g r e cube into rho. So this is t, and this is equation number 3. So I have obtained 3 expressions for time period t, this, 2, and equation 3. Let me just draw a line over here to separate this particular part. Right. So I have got these 3 expressions. Now what I am going to do is that I am going to think about a satellite which is moving very close to the Earth. So let us say that the satellite is moving very, very close to the Earth, and you know what we'll do. In that case, we will take h is equal to 0, because h will become very, very small as compared to Earth. So, and let us see how these 3 equations change. So we'll look at the 3 equations one by one and see how these equations change. So the first equation that we had was t is equal to, the first equation was t is equal to 2 pi into square root of r e plus h whole cube upon GME, right? And if I take h is equal to 0, h is equal to 0, so I'll get r e cube, and therefore for h tending to 0, I'll get t is equal to 2 pi square root of r e cube upon GME. Right? The second expression that I had got was t is equal to 2 pi square root of r e plus h whole cube upon GRE square, and if I take h is equal to 0, r e, I'll get r e cube, r e square I have over here, so this will become equal to t pi to square root of r e upon g. Right? And the third expression that I had was t is equal to square root of 3 pi r e plus h whole cube divided by g rho r e cube, and if I take h is equal to 0, r e cube will get cancelled, and get t is equal to square root of 3 pi upon g rho, 3 pi upon 0. So for h is equal to 0, time period of, or period of revolution is these 3 equations, so we can use any one of them. Let us say we choose this equation, right, and I can put values over here. So t is equal to, I am choosing this particular equation, so I'll get t is equal to 2 pi into square root of r e. Now r e, radius of the earth, can be taken as 6.3 into 10 raised to 6, and g is 9.8, pi is of course 3.14. so if I do this calculation, I'll get approximately 5063 seconds, and that is equal to nearly 84 minutes. So what I conclude from this is that a satellite which is moving or revolving very close to the Earth's surface has a period of revolution of 84 minutes. And in the previous video, we saw that the same satellite would have a speed of nearly 8 kilometers per second. So what I'm concluding is that v is equal to 8 kilometers per second and t is equal to 84 minutes approximately for a satellite revolving very close to the Earth's surface. Okay, so we have obtained v and t. We have obtained expressions for v and t and also found out values of v and t when the satellite is revolving very close to the Earth's surface. Thank you.